And the final part of this topic, P4.6 parallel circuits. Again, I've highlighted the key rules you need to remember in yellow. So the first I'm going to look at is the total current through the whole circuit is the sum of the currents through the separate branches. So we see in the parallel circuit, it's not just one loop, there's different branches to it. So this circuit on the left shows how you can investigate the current through two bulbs that are parallel to each other. So I've got two ammeters, I've got one ammeter there, one ammeter there, and I've got one here. So this is on the main sort of branch going round, and I've got two branches separating off here, and I can use these readings to investigate how the current changes around the circuit. So you can use ammeters, which measures current, in series with the bulbs, so next to the bulbs, so remember series means next to, and the cell to measure the current for each component. So this will measure the current through the cell because it's in series with the cell. This will measure this bulb, this will measure this bulb because it's in series with that. The reading of the ammeter A1, so the one on the series with the bulb, cell even, is equal to the sum of the readings from ammeters 1 and 2. So A1 equals A2 plus A3. Okay, moving on to potential difference. So potential difference in a parallel circuit. So for each component in parallel, the potential difference across each component is the same. So I've got another diagram here. Ignore this bit at the bottom here because I run over. So I can see I've got two components, Y and X, and I've got two voltmeters measuring the resistance across them, which is voltmeter 1 and voltmeter 2. So the two resistors, X and Y, are in parallel with each other. A voltmeter is connected across each of the resistor. The voltmeter across the resistor X shows the same reading as the voltmeter across resistor Y. This is because each electron from the cell either passes through X or Y, so it delivers the same amount of energy from the cell, whichever resistor it goes through. So basically when the energy gets to this point, it will then split off in equal amounts and one will go through resistance X, one will go through resistance Y. So that's why those readings will be the same. Remember not to get confused between potential difference readings and current readings. Okay, so remember these will be the same in a parallel circuit. These you'll need to add together in a parallel circuit, so don't get confused. Parallel routes. So this shows where the electrons will flow. So you can think of a parallel as kind of a bypass, so something that goes around, not through something. In the same way that for components in parallel, charge flows separately through each component. So it doesn't go through one then go through the other, it goes through separately. So it'll come in this end, go through X, come back down out that way. It won't go through Y as well. The total flow of charge is the sum of the flow through each component. The flow of charge per second through each component is the current going through it. And then just continuing on. So calculations on parallel circuits. The components in parallel circuit have the same potential difference across them, which is why I've got the same voltmeter readings. The current through each component depends on the resistance of the component. So if it's got more resistance, less current will be going through. So the bigger the resistance, the smaller the current. And to work out current, we should know this equation already. So current equals potential difference divided by the component resistance. And remember, there's different letters that represent different things. Don't get confused with the unit letters. Okay. Rules for resistors in parallel. So the total resistance of two or more components in parallel is less than the resistance of the resistor with the least resistance. So if you've got a resistor that's quite low, you can't have any more current going through than that. So adding more resistors in parallel decreases the total resistance because the total potential difference is the same across each resistor. Remember, that's different to in a series circuit. So adding the extra resistor in parallel increases the total current entering the combination. because the total resistance is equal to the potential difference divided by the total entering the combination. So what I mean by combination is which part of the circuit is going through. The total resistance is less than it was before the extra resistor was added. So I'm just going to show you a worked example of that. So we've got a diagram here, figure 3. So I've got one in the picture. So the circuit in diagram figure 3 shows 3 resistors. So we've got one here, one here, one here. So resistor 1 equals 1 ohm, resistor 2 equals 2 ohms, and resistor 3 equals 6 ohms, and they're connected in parallel to a 6-volt battery. So if we were to calculate the current going through each resistor, we'd use the same equation I mentioned earlier. So current divided by potential difference, current equals potential difference over resistance. So that would be for 1, it would be the 6 divided by the 1, because we know that the current is 6, it's got a 6-volt battery there, so we know that the current going through resistor 1 is 6 amps. Moving on to number 2, we know that that's got a I've got a current reading of potential difference of 2 ohms going through it, so it would be the 6 divided by the 2, and that means it's got a current of 3 amps going through it. And the final one, we know that there is a potential difference of 6, and we know that the battery reading is 6, so 6 divided by 6 is 1 amps. So that's how you'd work that out. And then if we want to do part B, so the current flowing through the battery, we need to add all of those together, so it's a total of 10 amps going through the circuit.